Live from our Windy City studios. This is Chicago Python Tonight. My name is Anais Dotis-Georgiou. I'm going to be your host this evening. I'm also one of the organizers of Chicago Python. Welcome to tonight's event. Let me just share my screen. So before we do get started, I want to make everybody aware of our code of conduct. Anytime you're interacting in a ChiPy space, be this on our YouTube comments, in our Slack, on our Twitter, like in our GitHub, you're gonna have to follow these rules. So just this, like the gist of it is just be respectful of other people and treat them the way you would like to be treated. So let's get started. So what is ChiPy? ChiPy, or the Chicago Python Users Group, is a Python community that was started back in 2003. We've grown from our humble beginnings of a few folks meeting like once a month to an organization that has around 6,000 members. And every month when we're meeting in person, we hold two to six events. On top of our monthly meeting, which we call the main meeting or the Dunder main meeting, we have special interest groups that are focused in on more niche areas of Python. There's the finance SIG. There's this one, which is the data SIG. We also have a special interest group for web development and DevOps. And a year ago, we started an algorithms and data structures SIG. We're going to help you get better at those interview type questions in that one. Do you want to make everybody aware of our upcoming events? Our next event is going to be the WebDev/DevOps SIG. That's going to be happening on Tuesday, August 4th. Currently, we have two talks lined up. One about Flask and how much of a micro framework it actually is. In my opinion, not that much. And then another one of the members of our community, he's working on this Telegram bot that was written in Node, and then they actually migrated it to Go. So it's going to be telling that story of a migration. I know it's not Python, but these kind of stories, they're really relevant just towards like software engineering best practices. So really excited to hear something about that. Our next algorithm special interest group is going to be on Thursday, August 6th. And then our next main meeting is going to be on Thursday, August 13th. We are still looking for talks. I'm looking for a short talk for the WebDev SIG, and we're looking for 2 talks for our main meeting. Please don't make me talk again. Like I really want to have other people in our community share their knowledge. So if you'd like to put together a talk or just have an idea, don't know really what's going on, reach out. I would love to help you get started. So do want to make some announcements. We recently revamped our mentorship program and released it. It's called the Buddy Mentorship Program. So if you go to chippymentor.org, you can sign up with your GitHub and then sort of fill out your profile, like talk about the things that you know, the things you're trying to learn, and give people a sense of like what you like to do as a programmer. Like if you like maybe data science, you like web development. Also sort of talk about like what you're like working on currently and what things you would like help in. Like this mentorship's really going to help you be more self-directed. So it's like if you have that structure ahead of time, it's going to make you a little bit more successful. So what else is going on in the world? I don't know if anybody saw, but Twitter just got hacked. A bunch of accounts posted messages where they were telling their followers to send money to a wallet with the claim that the user would double that Bitcoin. Unfortunately, this did hit a little close to home. The Chippy Chipmunk just sent out a message earlier. Hopefully nobody got hacked and had their Python 3 code converted to Python 2.7. But the hacker did get one thing right. This is going to be our best meeting ever. Speaking of which, let's talk about tonight's schedule. Our first talk is going to be by Anais Dotis-Georgiou about Facebook Prophet and InfluxDB. Our next talk is going to be by ChiPy community member Ray Buhr talking about how to use Facebook Prophet in production. And our final talk is by Sean Law, who's going to be going deep into a new library for time series analysis called STUMPY. I do want to make everybody aware we have a live comments feature. So enter in your your comments. You can interact with folks during this live stream. If you do have questions, please ask them there ahead of time. There's around a 20-second delay, so we can just have those queued up so we're not really dealing with some dead air. Where can you find ChiPy? If you go to this link, you can sign up for our Slack workspace. We have around 2,000 members. We're having conversations about pretty much anything in the Python ecosystem, both happening locally as well as things happening around the world. All this information, we also have a Twitter, which was recently hacked, as we just learned. It's at Chicago Python. All this information plus more is on our website, chipy.org. I mean, like, our account didn't get hacked. That was a pretty bad name. All right, let me bring on our first speaker. Welcome, Anais.
Hi, thank you so much for having me.
Yeah, we're really happy to have you. Can you please introduce yourself to our community?
Sure. Hi, everybody. My name is Anais Dotis-Georgiou, and I'm a developer advocate at InfluxData.
Awesome. Yeah. So can you please talk about like how you first got into Python?
Sure. So I was actually in biotech for a little bit, and I was programming this liquid handling robot to diagnose babies with autism. And I was doing most of the lab work, but I got kind of jealous of the data scientists because they seemed to be doing what looked like the fun work to me. So they sort of started introducing me to Python and the scripts that they were writing to actually detect the anomalies in the data to try and perform this prenatal testing.
Cool. So yeah. You are doing like a lot of time series analysis, I imagine, but is there anything else that you're like sort of interested in the data science ecosystem?
Oh, for sure. I really like computer vision projects. I've done some hobby projects with that. I also love NLP. I mean, I'm really a fan of like all data science, to be honest, because I love math. I mean, I think that's probably what drew me to data science and then to Python was just my love of math.
I mean, it's awesome to hear that like people love math. It's like, I never heard that, but it's like I'm hearing that more and more every day. So it's fantastic. So a lot of our community members have been dealing with sheltering in place. In Illinois, we recently started opening up. They are doing like indoor service with like social distancing. But it's been difficult. Like we've all been like not really interacting with folks. How have you been handling just being sort of shut in and locked down?
I think I just am feeling really grateful that like I'm in an industry that is able to pivot and be agile and work remote. So I'm just trying to take this time to just kind of appreciate like simple pleasures and enjoy the slower pace. I think when it's gone, we might actually feel a little bit of shock from like reintegration. So, you know, I don't know. I'm just trying to stay positive, I guess.
Yeah, I mean, like I was out a couple days ago, and it's like I didn't really know how to order food anymore. It was just it was a weird experience, but I'm sure it's just gonna take some time to get back. Cool. So, are you all ready to go with your talk?
Yeah, absolutely.
Okay, cool. Let me just share your screen. Anais, please take it away.
Okay, great. All right. So today, all about time series databases and using Facebook Prophet to create univariate time series forecast. And this talk will go from the macro, we'll start off kind of asking ourselves, what is time series? Why do you need a time series database? Then I'll introduce InfluxDB and how it can help you to handle your time series data. And then we'll actually start talking about why it is that you might want to use Facebook Prophet, the advantages of Facebook Prophet, why it was built. Then we'll talk a little bit about how it works. And then finally, I'll demonstrate to you how you can write data to InfluxDB, and then how you can use the Python client to query your data and create a simple prediction. I do want to specify that this data set in the example is largely replicated from the quick start example from the Facebook Prophet repo. So if you want to find that work and that, you can look there as well for it. And I won't be demonstrating too much of the nitty-gritty about Facebook Prophet, but luckily this whole meetup is organized so well that in the next talk we'll get to learn more. So yeah, I'm really excited about that. So a little bit about me. As I mentioned, I'm a developer advocate at InfluxData. For those of you who don't know what a developer advocate is, it's someone who tries to represent the community to the company and the company to the community. So I spend a lot of my time creating blogs, tutorials, proof of concepts, giving talks, answering community questions, taking product feedback, giving it back to product, and also demonstrating and sharing the work that engineers do, which is actually probably my favorite part of my job, just because I like to have the opportunity to give these awesome engineers the sort of the publicity that they deserve and highlight their work. That's even though I didn't do it, so I get to share it with everybody and kind of get to brag for them. So yeah, and then if you want to follow me on LinkedIn. My parents actually gave me 5 names, so that's what I stuck with on LinkedIn. So Anais Dotis on LinkedIn, and then my Twitter is Anais Dotis. So let's just start from the beginning. What is a time series? It's probably what you think it is, or what you might already know that it is, which is just a series of data points that are indexed in time. And so common examples include things like weather or stock prices, but the reality is that time series data exists absolutely everywhere. There might be something sort of philosophical about that, and something to do with space-time, but I'm not going to go that deep. But basically, we find time series everywhere. We think about IoT monitoring, and we think about software teams who are expected to move more quickly and test more frequently and release more frequently and test earlier and improve the quality of their code. So they need to do things like be able to collect a whole bunch of metrics on their machines, their VMs, their containers. They need to be able to look at system stats. They might need to be able to track third-party integrations. They might need to perform application monitoring. They might need to monitor their CI/CD pipelines. So, sorry, I talked about, yeah. So DevOps monitoring is obviously a huge source of time series data. And being able to have visibility into the health of your systems is what enables organizations to uphold their SLAs, right? And then when we think about IoT monitoring, went in reverse, but when we think of IoT monitoring and we think about the fact that there are going to be, what is it? I think it's 25 billion IoT devices, active IoT devices by 2025. I mean, that's insane amount of devices. And when I think IoT, I mostly think sensors, and sensors monitor our physical environment. And so all of that data is also time series data. But time series isn't just limited to IoT monitoring and DevOps monitoring. It also exists in business analytics, in fintech is a huge source, also in biotech and healthcare and agriculture and retail. It's pretty much everywhere. So you need a special way to collect, store, analyze, and visualize time series data, because the way that people interact with time series data is fairly unique. When we think about time series data, we're either concerned with what's happening in the present and we need to collect it in real time and act on it in real time, in which case we need a method or an agent that will be able to collect data from sensors or hosts or containers efficiently. And we also need to be able to store that massive amount of data in a database that's optimized to handle really, really high ingest rates and really high query loads. And so you need some sort of time series database for that. Also, time series databases in general, they typically have integrated features which allow you to downsample your data, because it's pretty rare that we want to retain the full precision of our data for a long period of time. So we need some sort of feature that exists like that. Or we might even just decide that after a certain amount of time, this data isn't even useful to us anymore, and we need a way to automatically expire it. Also, when you think about observability and visualization of your time series data, you need to be able to have access to a visualization library that incorporates algorithms that allow you to plot hundreds of thousands of time series data points in a fast and efficient manner, and that will render those visualizations quickly. So you need not only specialized collection agents, databases, but also specialized dashboarding capabilities and visualization. So I will introduce InfluxDB just briefly. InfluxDB is InfluxData's main monitoring platform, and it consists of two components, Telegraph and InfluxDB. Telegraph is a collection agent. It's written in Go, and it's plugin driven, and it's database agnostic. So with a single config, you can gather data from a variety of different sources and send that to any database of your choice. Well, not any, but there's a lot of different outputs. So if you are just simply looking to collect data and you don't know how, and you can't think of a good way to do it, I highly recommend checking out Telegraph, because it's also open sourced, and so is InfluxDB. And InfluxDB is a purpose-built database, a visualization, and a query and task engine. So you can create alerts and notifications. You can create tasks which will run various queries or user-defined functions on your time series at scheduled times. And you can downsample your data, or I don't know, create custom anomaly detection algorithms and apply them periodically. So now let's talk about Prophet and what it is, why it was created, and what it aims to achieve. So Prophet was basically created because time series forecasting is hard. To completely automate forecasting techniques is very challenging. And also a lot of traditional forecasting techniques, and statistical techniques, or even neural nets are difficult to tune, or they're oftentimes too inflexible to incorporate useful assumptions or deep domain expertise. So Prophet aimed to first address that problem. Facebook wanted to make a time series forecasting library that would be flexible and easy to tune. And then the second is that time series data is extremely unique. And it's unique because it exhibits this property called autocorrelation, which means that one portion of time series is oftentimes correlated to another portion of itself at a previous time. So that's kind of the definition of seasonality from a math perspective. In other words, like if we think about sales, these sales on one given Friday will probably mirror the same sales on another Friday. And this feature of time series makes it especially tricky to determine what sort of algorithms you should use for forecasting. It makes it really hard to also evaluate the prediction accuracy of your model. For other models, when you try and like predict class, for example, you might be able to use linear regression to make sort of predictions, but you can't actually use linear regression and then use like the RSME or the distance between the residuals between your prediction and a linear regression to model your prediction accuracy, because basically linear regression assumes that your data doesn't have correlation. So you can't actually even use that with time series. So my whole point is that time series is like very different type of data, and a lot of data scientists might not have specific training in time series. And so Prophet wanted to help data scientists and data science departments and organization have access to forecasting algorithm without having to necessarily have this deep domain expertise. And finally, what Facebook Prophet aims to achieve is that because it's easy, the idea is that a lot of people will be able to use it. And secondly, it allows you to handle idiosyncratic features. And what I mean by that is that a lot of statistical forecasting algorithms require that your data is a regular time series, meaning that the interval between each time series point that you get is equal. But the reality of the situation is that life is messy and that we don't typically have data that's that clean. And so in order to apply a lot of other statistical forecasting methods that depend on the assumption that you have regularly spaced time series, is you need to do a data preparation step beforehand and perform some type of interpolation so that you can convert your regular time series into a regular one. And Facebook Prophet just eliminates that requirement or that step. So that's another way in which it makes it easier. And just by contrast, some algorithms that require that you have regular time series include things like ARIMA or triple exponential smoothing, just to name a few in case those ring a bell. So now let's briefly talk about how Facebook Prophet works. So in essence, it's very similar to double or really triple exponential smoothing in that it takes the regressors of the time series, in other words, the sort of dependent parts of a time series, and it separates them out, the different components of a time series, and then creates predictions for them independently, and then sums them back all up together and to produce your forecast. So the formula is briefly described as y of t, which is our prediction, equals to g of t, which represents little piecewise or linear or logistic parts of our time series, plus the seasonality pattern, s of t, plus h of t, which are any holidays that are given by the user. So for example, if you were looking at sales, maybe you might include holidays, like Thanksgiving and Christmas, et cetera. And then finally, the residuals. And the residuals are just, if you have your original time series and you separate away basically the linear or logistic growth, so the trend, and you separate the seasonality and you separate your holidays, whatever you're left with. So basically kind of noise. Or errors. So it incorporates all these four elements, makes individual predictions, adds them back up together, and that's how you get your prediction. So today I will be teaching you how it is that we can set up Telegraph to write some of our data into InfluxDB, and then we will use the Python client to query our database, and then we will convert that data into a data frame. And finally, we will make a forecast with Facebook Prophet. So the very first step we need in order to use Telegraph, once you've installed it, also Telegraph and InfluxDB, they install as a single binary. So once you have installed it, you need to gather some parameters. And you also need to gather these parameters not only for Telegraph to write data to Influx, but also so that you can use the Python client to query data from your instance. And these include gathering your, what is known as your bucket, your token, and your organization. And so this is a view of the InfluxDB UI under the Load Data tab. And you can see we have all of our information there. A bucket is basically where you write your data to. And then the organization is the organization that you set up, which is multi-tenant. And so, yeah, it's just your organization. And let's see. So yeah, that's where you'd find all those variables or all that information. Or alternatively, you could also use the CLI to find that. But to run Telegraph, all you do, the first step is to generate a config. And the way that you do that is you specify Telegraph, and then you use the input filter to specify which plugin you want as your input. And we're going to be using the file plugin. And then you also want to specify your output filter, which will be InfluxDB v2. And then you use the config flag and to specify where you want this config to go, and you store it into the configuration file of your choice, which I'm naming prophet_data.conf. And then we run Influx, the CLI, and we can pass in our token and our org name and use the bucket find command to actually find our buckets as well this way. So that's just another fun fact. And then to actually run our Telegraph config, we simply pass in our prophet_data.conf with the config flag --config. So this is what a Telegraph config looks like. It's pretty simple. If you want to write data to Influx, you simply need to specify the URL where Influx is running. You need to provide your token, your organization, and your bucket. And then actually I'm missing a slide, I just realized, but in order to write the data, the input portion of the config, you simply specify the pathway to where your CSV lives, and then it can write that data from CSV, since I was using the file input plugin. Well, let's just move on to Python, because that's what we're here for, right? So the very first step to use the InfluxDB Python client is to first import our packages. And so we will import our InfluxDB client. We'll also make sure that we have imported pandas, and we might want to specify the write option for the client as well. And in this case, I will be making my writes synchronously, but you can also make asynchronous writes. And after I've gotten my authorization parameters, and I've stored them in a variable called token, and I also have my URL, and I also have my bucket ID, I can now simply just instantiate the client. And then the next thing I need to do is to generate a query with Flux. And Flux is InfluxData's scripting language designed for querying and analyzing and acting on data. So this query I'm storing it in the variable query, and it looks like the following. I specify from bucket, the bucket that I'm writing my data to, which is Facebook Prophet. And then I specify the range from which I want to query my data from. And then I'm going to specify the filters that I want to filter for. And my data set is actually going to be page views on a Wikipedia article of Peyton Manning, who is a football player. And I don't remember for which team, but I probably should know that. But I'm not a huge football fan. So apologies in advance. I guess I'm not a good Texan. Anyways, and then so I'm going to filter for the views, which is my measurement, and the field, which is Y. And I chose the field of Y because that's actually what is required to be the column name of the value or the value that you want to make a forecast on in your data frame when you use Facebook Prophet. So that's why I wrote my time series data with that field name. And then I can return the results after I use the query method, where I supply my organization and my query. And I will store those results in the variable results. And I just wanted to show you sort of what that data looks like raw, just so that you know how I'll kind of have a preview into how the client works. But I actually don't recommend iterating through the tables and looking at the data this way, because there is a query get data frame method as a part of the client that you can just return the data as a data frame directly. But I did want to share with you what the raw results look like, because it is something that's kind of unique to Influx, in that Influx stores all of the time series data based off of a group key and splits the data sort of into tables. So even though InfluxDB is NoSQL, it has this almost like table relational feel, and Flux allows you to interact with the data in a very similar feeling. And so you can perform things like joins, you can do math across measurements, and you can perform complicated groups. And so that's kind of why I just wanted to kind of demonstrate like the raw results from the client. Which of course we could convert into a data frame like so, but the way that I really recommend doing it is that if, for example, instead we were, let's say, querying some system stats, then we can simply use the query underscore data underscore frame method of the query API and return our data directly into a data frame. So yeah, that's what I would actually recommend. And then you can use Pandas data frame head function to return the first n number of rows or 5 number of rows. So now let's get into how it is that we'd make a forecast with Facebook Prophet. So Prophet really couldn't be more simple. So we start off by just instantiating a new Facebook Prophet object, and any settings that you want to put into your forecasting procedure would be passed into that constructor. So if you want to add things like holidays, if you want to add saturation limits or maximums and minimums, you can do that. So what I mean by that is if you know that your system is bound by physical limitations, like maybe you're in a chemical plant and you're looking at a heat exchanger, and you know if the temperature, if it exceeds a certain amount, you're going to have some sort of, or it can't exceed a certain amount because because of the system itself, then you can include these saturation limits. So that's another thing that another feature of Prophet that you can take advantage of, for example. So yeah, you fit any of your forecasting settings into the constructor, and then you call the fit method on your data frame. And this is our actual data that looks like the page views. So the left-hand column here are the page views, and DS is the date. And DS is actually what you need to name the time column of your Pandas data frame. And so once you make the fit, and fitting doesn't take very long, like just a couple seconds, then you need to create a future data frame so that you have a data frame with empty rows so that you can actually make a forecast onto that data frame. And so you use the make underscore future underscore data frame method, and you pass in the number of periods that you want to be able to extend your data frame to. And so if we sorry, let me go back a second. So actually, if we look, I made a mistake. I'm so sorry. I'm feeling silly. So if we look at the the left-hand column, that's actually just the index. And we can see that we don't have any y values because it's empty, because we just extended the dates out into the future, but we don't actually have any future forecast. So now we're able to actually like make a forecast onto this empty data frame. And maybe it would help if I show you real quick like what our data originally looked like. So our original data is the pink line with daily views, and the field is Y. And so now we can simply call the predict method on our future data frame, and it will assign each row in the future data frame a predicted value. And it names that predicted value y hat, and it also supplies confidence intervals y hat, y lower, which you can also change the confidence interval level if you choose, as well as other statistical aspects about your forecast and about your fit. And so then we can use the Python client to write our data to InfluxDB. And I'm actually running out of time, so I will skip that, but basically all you need to do, I'll just like briefly describe it. So instead, when you want to write, it would look like client.write_API.write record equal, and then you pass your data frame in as your record, and that's how you write your data to InfluxDB. And you also specify the bucket that you want to write your data to, as well as your measurement, and that's all that you need to do. So yeah, I wanted to also mention some other things that Prophet can do. I recommend just taking a look at the documentation because it can do a bunch of different things. Like I said, you can add holidays, you can create saturation thresholds, you can also adjust the change point prior scale. So what that means is that when Facebook is trying to kind of map out the linear and logistic trends of your time series, it will sample time series at a different scale. So you can either say like take a lot of samples or fewer samples, and that will kind of essentially have the effect of like making your forecast like smoother or not. So that's another really useful tool. And then you can also add multiple regressors to your time series as well. And the way you do that is you simply add another column. So if you had your Y column in your data frame that has your actual values, you would have another column that would just be your regressors. I believe that's how you do it. And then you can make the fit. As long as your predicted, the values that you want to predict on has the column name Y, then you're good. And then I wanted to talk a little bit about the Python client and address a question that I get a lot, which is like whether or not machine learning needs to be carried out server side. And I just wanted to, my opinion is that it doesn't, for two reasons. One is that this Python client is extremely performant. You can query like 4.6 million points in 21 seconds. I did it on my machine with other processes running, not with the same benchmark conditions, and I was able to query over 1 million points in like 12 seconds. So yeah, it's really fast. And then secondly, I think just in terms of thinking about like what's the best way to maybe execute or apply machine learning in production, I think it makes sense to pull your data out of your time series database in general, because time series databases should really be considered more of a time series data lake, whereas when you want to apply machine learning, you might want to do that in a data warehouse and isolate those workloads. I will say some disadvantages coming back, because I talked a lot about the advantages of Prophet, but some disadvantages include that in order to make a successful forecast, you need to forecast you need to have an entire cycle, ideally. And so that can be a lot of data. Like in contrast, an advantage of using a neural network is that you might be able to save the weights and perform incremental training, which could be a lot more lightweight. So I think those are just some of the pros and cons, but I'm sure we'll learn a lot more about how to use Facebook Prophet in production. But I will say that if you're going to only perform univariate time series forecasting, then you definitely want to use the statistical method, because they outperform neural networks in terms of prediction accuracy. And then here are some resources, some examples for using LSTM, for using Keras. And then also, if you have questions about time series and time series forecasting, I encourage you to go to our community channel, community.influxdata.com, and ask me any questions you have. I'd be happy to talk and exchange ideas. We also have a Slack channel. And then here's some more resources for some differences in some basic data science tools and the Python client. Thank you. Actually, I can't hear you.
Oh, sorry. Yeah, my mic was muted. Yeah, thanks for pointing that out. Can we please give Anais a round of applause in the chat? I just posted in my my clap emojis. That was fantastic. We do actually have some questions. So the first question is, what kind of dimensionality can InfluxDB handle?
Dimensionality?
Yes.
So you can have, I'm wondering if that's the same, if you're asking the same thing as like series cardinality. So you can have a huge amount of different time series ingest capabilities. I think I have some silly slide that feels very marketing-y in here. So if you have like a series cardinality of 10,000, then you can have over 700,000, right? Over 700,000 points per second. If we're thinking about dimensionality, it's really up to you and what your time series looks like. Yeah.
Awesome. So we do have another question. How do you choose periods? Is there something that you do, maybe observe them visually and then try it with the specific settings, or like maybe like a trial and error type thing?
So I think a lot of people like to see if they can, visualizing their data always has a lot of value, but a typical approach someone might have to automatically detecting seasonality in their time series data is to create an autocorrelation plot, and then maybe use Pearson's correlation coefficient on that plot to determine whether or not you have, that's like a quantitative way of determining whether or not you have seasonality.
Okay, cool. And also, you were mentioning that Facebook Prophet can handle holidays. Can it also treat intraday times as special?
It can. You can also develop schedules too, where you can prioritize and increase the weights during certain periods of the time of your day. So if you know that operational hours are from 8 to 5, then maybe that data gets more of a weight, and you can tell Prophet to kind of ignore the data outside of particular times.
Okay, awesome. And so you were talking a little bit about like the workflow of setting up like InfluxDB and how people use it. So what sort of just like, is it deployed out using like a cloud service, or do people install like their own version? Like how do people manage InfluxDB?
Yeah, so we have a fully managed cloud service with a free tier as well that's scalable and elastic. But there's also the open source version. So sometimes, like if you think about IoT application developers, they might be using a combination of both, where maybe they're doing some IoT processing at the edge. Maybe they're even using the STUMPY at the edge too, for example, and then maybe sending aggregated our data back to Influx and storing all their data there. So it can be a combination.
Okay, cool. I think that's it for all the questions. Can we please give Anais another round of applause in the chat? Before we do let you go, do you have any action items or words of wisdom for our community?
Words of wisdom: stay curious.
I like that. Is there anything you're curious about at the moment? Sort of just to pry a little bit?
I'm super excited about this talk today because I have been reading a lot about STUMPY or Stumpy. I'm sorry, I don't know the right pronunciation, but I'm super excited about it. I've been spending my whole week learning and reading about it. So that's what I'm been into.
Awesome. I like that. Well, I'm glad you're excited about this talk. Your talk was fantastic, and thanks again for joining our live stream.
Thank you so much for having me.
All right. So that was Anais Dotis-Georgiou, and she was talking about how to use Facebook Prophet in conjunction with InfluxDB. Next up, I am going to bring Ray Buhr onto our live stream. Welcome, Ray.
Hey, what's happening?
Hey, Ray. Ray's one of our fantastic ChiPy community members. He's very involved in the community. He's been a mentor doing all this stuff. But can you also introduce yourself to folks that might not know you? Do we lose Ray? Do we lose me? All right, we are back. Ray, can you hear me?
I can hear you. Sorry, my work and decided to time out, and it kicked me off the internet.
Yeah, no worries. I mean, these things happen. It wouldn't be
that's my bad
without any sort of technical difficulties. Yeah. So, can you please introduce yourself to our community?
Yeah. So I'm Ray. I work at Braintree, a PayPal service. I'm a data scientist there. I've been there for a little over a year and a half. I'm on the data research and analytics team. So we try and leverage data to make products smarter. I'm not selling this very well. No, but yeah, that's what I do.
No, it sounds great. Of course, you're using data and you're helping your products get better. So can you talk a little bit, how did you first get introduced to Python?
Yeah, so one of the first jobs I had out of college, real professional career jobs, I worked as a data analyst for this consulting company. And yeah, our stack was Excel and SQL. So I'd write a query where I would steal somebody else's query and hope that it was right. And then I would put it in Excel and try and give people insights or make dashboards from that. Mm-hmm. And it was just a ton of work. And I did the same thing every day. And I would recreate the same report every week and send it out. I was like, there's gotta be a better way. I Googled it, you should use Python. And then I started learning it, and now I'm here. Just kept going and never stopped. That was awesome. 2011. So
just to dig into that a little bit more, a lot of folks in our community have been making the jump from data analysis into more of a tech role as a data scientist or maybe a developer. I myself have made that same transition. Excel was my life. So how did you go about sort of learning more of these hardcore math skills?
I was always good at math. I went to the Illinois Math and Science Academy. I've always been really, really good at math. So I'm not sure how to answer that.
No, fair enough. No, math comes and goes. I think the one thing that sort of helps me is if you just sort of keep plugging away, I think in math and in software, the first time you see a concept, it might be difficult, but if you keep sort of seeing that concept over and over again, those things become a little bit easy. But like we're all sort of dealing with like sheltering in place. Like I've been hanging out doing this like YouTube thing. My setup keeps getting better and better. Stay tuned till the next main meeting. I got a surprise coming up. But how have you been dealing with sheltering in place?
It's been interesting. I just had my wife and I just had a kid in February. So like,
congratulations.
Yeah, thanks. I kind of been sheltering in place, so like not doing work and then coming back to work and then taking another break from work. It's been really weird to alternate between being like stay-at-home dad and full-time employee from my bedroom. Yeah, I don't know. I don't have a good answer for like how I've been doing it. It's just taking it one day at a time because everything is new right now.
Yeah, I could only imagine like what this must be. Like it's just the world is changing and you're not sure what's going on. But that's enough about like COVID and about the pandemic. Are you ready to get going with your talk?
Yeah, sure.
Let's get your screen shared and we can start it up.
Okay.
Awesome. Ray Buhr, please take it away.
Cool. Yeah, so these slides, I literally made them almost a year ago, August 16th. PayPal has this internal group called the Machine Learning Guild, and this talk was part of the very first one, the very first meeting of the group. So I'm gonna have to like remember a little bit how this stuff works, but I think it will be okay. Anyway, so yeah, you guys know all that stuff. Come on, there we go. So first, I'm gonna go over like the background, like why did I need to do time series forecasts? Like what was the business reason? What were like the challenges with the data that we had? What were we trying to predict? I'm going to talk about like the model that I came up with and kind of then talk about like how the results turned out. And then at the end, I got time for Q&A, and I got like a couple like things that I don't have in slides, but I want to talk about. Like basically, I don't want to put them in writing, but I want them to be known. So like background, PayPal, Braintree, we let people pay for things online. So it turns out like in the background, a lot of what we're doing is just duct taping banks together. And so we had this project with Australia working with the National Australia Bank. It's the biggest bank there. And like the long story short is we were trying to we ended up like manually moving money around for a while. And the finance team had put together this model in Excel, and it was just really bad. So like the one on the right, that green line is like the actual day-to-day account balance. And then the blue line is what their forecast said it was going to be. So you can see like not even close. In addition, like to it not being a good forecast, they also ran into like the hashtag big data problem. They were writing a query against Redshift to get the data. It got to be more rows than Excel could reasonably handle. I think it was like up to almost like half a gig of size for the workbook. And so like they had to like rent giant servers just to run this thing in Excel. It was pretty funny. But so I stepped in and I was like, yeah, I think I can make this better. So the modeling challenges, like what was the hard part? So it turns out like I was trying to forecast 1,000 different customers, and we call them merchants because they're businesses that have their own customers, but there are customers. Anyway, so we have like 1,000 ones. I'm trying to forecast all of them. So really what I thought was it's better to have a different forecast for each single one, but the finance team doesn't care about the individuals. They care about the overall total that's going to end up in that bank account. So, well, I probably should have crossed out those two big merchants because they call them out by name. But my point was like those two big merchants are way bigger than all the other customers we have in Australia. So they have like really significant effects on the overall total that would have to be weighted higher. And then like lastly, like there are really weird holidays in Australia. So like they have their normal bank holidays, but for the customers that we have, there's like sporting events that last for weeks on end that really affect like these merchants who let you gamble on sporting events. And the sporting events are like not stuff that's popular in the US. So it would be things like cricket or like horse racing, just gigantically popular in Australia. On the data side, like we had really good data pipelines for everything that we controlled, like when transactions were started and finished. And we had really horrible data pipelines for when things actually happened on the bank end. So a lot of like what we do is just create APIs. And so we'll send requests back and forth. That stuff was awesome. The data is perfect. So I get very fine-grained, accurate data for what we were trying to do. But what the actual results in the bank on the other end might happen like a week later, which is ridiculous. Like usually it's pretty instant within a couple seconds, but sometimes they'll come back a week later and say, oh yeah, by the way, we did complete that one. So you'll have to go back and update your record. Or we did reject that transaction. Sorry, we told you we approved it before. So kind of like I needed to have some flexibility. I needed to have a way to have like an error, like some uncertainty. So I decided to use Prophet because I was like, I don't really want to fine tune an individual time series model using ARIMA or any of the other like exponential time series smoothing. I didn't want to like use one of those kind of tried and true methods 1,000 times over and customize them each for it. I wanted something that was kind of be good enough automatically. And Prophet said it could do that. So like as Prophet pitches it, it's like accurate, automatic, tunable, and it's in Python. It's like checked all my boxes. So like I'm gonna go real quick over these. It's just about like what I wanted out of Prophet specifically and why I thought it was cool. It was like the seasonal decomposition. I needed that because all of the businesses, the 1,000 businesses I'm trying to forecast, they have different patterns. Some have very like week over week repetitive, some are month over month, some are like completely sporadic. And I needed to be able to split that out individually for them. And Prophet does that for you automatically. The change point detection, like some of the customers we have, they might not give us all of their transaction volume all at once. So usually you would think, okay, well, you onboarded this customer, they're going to start processing on your system. Great. But what ends up happening is they want to test like 10% at first. And then maybe 2 months later, they're going to bump it up to 20%. And then they're going to jump to 50%. And so they have these very step level increases. I didn't want to have to like create a time, like a hash table of the times of when they onboarded and increased their volume and look that up every time. I wanted the time series detection to just say, yep, step level change, new forecast starting from here on out. And Prophet does that. And then lastly are these like holiday effects. And this was brought up in like the chat for the questions on the last talk. And I actually had to make my own custom holidays for a lot of these people. Specifically, I talked about those gambling merchants. So like in the fall, I have, you know, whatever, these like 5 or 10 gambling customers. They get like a whole holiday for like those, you know, 6 weeks that it's important. And then everybody else has their own special holidays. So that might not be a traditional, like it's Christmas or it's Easter or, you know, the Independence Day or whatever. It could be, it's their biannual sale. It could be something very specific to the business that's not specific to the world overall. Cool. And then I wanted to like see if the regressions were additive or multiplicative. And it's basically saying like, is the trend increasing over time or is it pretty static? It turned out like this actually didn't really matter for me. Almost every single forecast I had was additive, which is kind of your traditional like linear pattern. But I wanted it just in case. In confidence interval. So this is what I was talking about where I needed to have some uncertainty. I needed to know like, all right, well, here's what it's forecasting, but also like it could be anywhere between these upper and lower bounds. So when I aggregate all that together, I might say today we should see, you know, $10 million go into the bank, but expect it to be anywhere between 8 and 12 in reality. Cool. So This is how it actually ended up happening. I had a very straightforward process. I set up a Google Sheet with our project managers, and they put in the migration plan, like when these new customers would start processing on the new platform, and then the data would go into our warehouse, which was Redshift, and I would query it and get all the data back for all of the customers. And then I would loop through all of them and generate a forecast for them individually. I'd combine all those forecasts into an Excel file, and then I would send it over to our finance team. We call them FinOps, finance operations. That's what that means there. And so, every week, the finance team would see this file show up in their network drive, and they would review it. And if it looked like things would be okay, they said, great. Hey, PayPal finance team, here's our automated forecast. It looks like things will be good. And if it looked like maybe we were going to overdraft, they would say, hey, can we have some more money, please? So that's kind of like how this actually got used. And on the right, you see my chart. Let me go back to the old one real quick. So here, green was actuals, blue is the old forecast based on Excel. It's pretty bad. Woo. Okay, and then here, green is actual, blue is my forecast. And you can see mine fits a lot tighter. Mine did kind of get a little wonky. Part of that is because the project manager migration plan in Google Sheets didn't actually happen the way they put it out there. So we were expecting more people to onboard, and they just delayed it. But for the most part, it's huge improvement, much more stable, much more reliable. Cool. So I know you guys cannot see this. It's tiny, but on the left, it's just the tree structure for my project. I've got a data folder. I've got a docs folder. I've got K2 AU forecast. That's my Python module. That's where all my code goes. I'll talk about that in the next slide. We need to concentrate on it for now. I have a reports folder. This is where the output from the forecast gets dumped. I have a scripts. So these are just random things that I think need that I would just say Python run this script and it'll automate something for me. It's not really part of the process, but it's more, glue work, I guess. And I have a test folder, testing that my functions work, that my the integration tests between the databases are good, networks, stuff like that. And then lastly, I've got that venv folder, and that's a virtual environment. That's the package that comes with Python 3.4 and on by default. So you can create specific dependencies private to your own project. I don't know if that's a good way to explain it. You guys can Google it. Cool. Anyway, so all right, I have all this code here. What do I do with it? Well, I set up a make file. Make is a tool to, I guess, automate a series of instructions. So I have a target install, a target refresh data, a target forecast parallel, and a target report. And they kind of do what those names imply. Install sets up PyEnv and the virtual environment and installs all the dependencies. Refresh data says, use that query template to go get data from Redshift and download it into the local directory. Forecast parallel then uses that file that we got from Redshift and loops through it and generates a forecast for each of the customers inside it. And it does it in parallel. And then report takes all of the outputs from the reports folder and combines it into an Excel file to drop into the finance team shared drive. I also had some make targets that were not really part of the automated run process, but they were useful for development. So I had configure, which is set up your passwords for Redshift and things like that. Any changes you wanted to make for environment variables. Clear, which just deletes all the files in the reports so that when you go and run the make report, it doesn't combine old files. I had a make progress just because when you're running 1,000 forecasts in parallel, I don't really know how far along it is. Anyway, I had IPython, which just starts up a REPL that's based from this venv virtual environment. and then make test, which would run all the tests, let me know if my code deviated or things weren't able to connect through the network or whatever. Cool. So the next thing I'm going to talk about is that K2 AU forecast module. Real quick, I'm just going to go through the files that are in there. I had a custom holidays.py, and this is where I was able to say, here's like the series of dates that are going to be the gambling season. Here are the dates and times for, I don't know, like any specific customer holidays. Like here's their biannual sale. Here's, their billing, their monthly like billing subscription date. And to make the custom holidays, all I did was create a dict, and I put the key name as like the name of the holiday, such as gambling season or, customer name, biannual sale. And then the values was a pandas data frame with a column DS. That was a date time that had the dates that that should be considered as variables as holidays in the model. I have a date calculator. This is just to do bank math. It's kind of dumb, but the Excel model had this function like Workday International or something, which lets you add and subtract dates, but like in business days, but for international schedule versus a US holiday schedule. And I could not find a way to do this in Python exactly, but NumPy has like a business day method that I kind of hacked. So that's what date calculator does. Forecast.py is like the meat of it. I'm going to present more on the functions there in the next slide. I have Japan holidays because we have a couple merchants that just do transactions in Japanese yen, and the dependency I used for different country holidays was really messed up for Japan. I have query template. That's just that's a SQL that goes and runs against Redshift. And then I have Redshift Connect, which is how to connect to that. And then lastly, I've got settings.py. And so in the previous talk, Anissa talked about like being able to plug in parameters to your forecast like constructor, like when you initiate the class. That's what settings.py does. It's a way to say like these specific customers have weird defaults that I want to set, and then everybody else will get a standard parameters. Cool. So that forecast module, the meat of like the work for building the forecast, I said merchant df, which is just like take that giant Redshift output and filter to just the specific customer that it's looking at. I have a daily data frame function, which sometimes the way I wrote my query, I would end up with like multiple days because there were different dimensions in my group by statement, and I didn't pivot them out. So this just kind of pivots it to get a by date data frame that has the columns that Prophet expects. Get holidays, kind of what it says. Like you pass it like what kind of named holidays you want to pull from the custom holidays, and it goes and fetches those dates and sends it into that to reuse in Prophet and building the model. I have trend forecast that just calls the dot fit on it. And I have predict forecast, which calls dot predict. And then I have the build the forecast data frame. And so really what this final thing does is it uses the forecast it constructed and then puts it in a slightly different format that finance asked me to do. So, Prophet has like your Y hat and all that stuff. Finance is like, I don't know what Y hat is. So I just like renaming columns. That's like the gist of it. Cool. This is an output. So normally I would just call make forecast parallel, but this is like what that command calls. It just loops through all of them. And so you can kind of see that when I did it one at a time, so I said, generate the forecast for this specific customer, and I gave them like plugged in their random UUID, and Prophet starts logging all this weird stuff. Initial log joint probability equals -7 points. They're like, I don't know what this is. So Prophet's built on top of this library called PyStan, which is an interface to Stan, which is like a statistical Bayesian modeling software. So yeah, I don't know. I tried to turn off logging so hard, and it just wouldn't let me do it. I couldn't override it. Normally, you should be able to say, hey, use the logging for this module and set it to just error. And the Prophet library actually has it hard-coded in that it's going to do info no matter what, which is, I think, a bug. And I tried to file an issue for it, and they said, yeah, it's not a bug, it's a feature. But anyway, like you can see, like my gold font here, calling each merchant's or each customer's forecast one at a time would take roughly 10 to 20 seconds. So it's not super long, but I had to do it 1,000 times over. I didn't want to sit there for 6 hours a day. I wanted to be as fast as possible. So I leveraged this tool called GNU Parallel. So GNU, the new like Linux software. And basically you just say new parallel, this text file of commands, and it says, well, how many CPUs do you have? I'm going to run that many at a time. So really cheap and easy way to parallelize Python. Cool. So the tools I used Microsoft VS Code as a text editor. Mostly I did that because I was pair programming with another guy on my team, and he was not very comfortable with Vim, which is fine. VS Code is awesome. It worked out really well. We could do like that collaborative live share. Like he lives in SF and I'm in Chicago. I told you about how I used Makefile. I use that for both the CLI and the automation. Run all of these steps back to back to back. The Python specific stuff I use. So I use Python 3.7.3. I use VN for virtual environment management. Obviously I use Prophet. I use pandas for data frames because Prophet expects them. But also pandas just makes it easy to query and pivot and reshape data. I use NumPy specific for the business day offset. I use this library work calendar. So remember how I told you that I made that like Japan holidays script or module? I actually push that up to this library work calendar as an open source contribution. So if somebody else wants to use holidays for Japan, they don't have to write it themselves. I use Black to format my code. I use PsychoPG to connect to Redshift. OpenPyXL for writing to an Excel file. I use PyTest for testing, and IPython as like debugging and REPL stuff. Cool, so that's like my talk. One of the things that I wanted to talk about was, why did you just write one query to Redshift and then hit that CSV file over and over again? Well, it turns out that Redshift has a limit of like 50 connections at a time, and most Redshift DB admins will limit each user to a certain number of slots or queues. And my user was limited to one slot. So at first I did try and write the queries to like run in parallel, but they just ran sequentially anyway because how our database is set up. So it's actually easier for me to write like one query and get all the data and then operate on the file output in parallel. The other thing I want to talk about is like, why didn't I do more specific modeling? Well, I had to do 1,000, right? So like that's a lot. But more importantly, I don't know anything about these businesses. I'm not like a time series expert. I really kind of just wanted the 80-20 rule. I wanted something that was good enough and that would, be better than the Excel model that they had built before. And this accomplished the goal 100%. The downside of this is, well, didn't you get some bad predictions in production then? Yeah, absolutely. When COVID-19 hit, whoa, we went from being like usually within maybe like 2% accuracy on the overall portfolio to being only like 85% of the total. The actual was only 85% of our forecast. And that 15% swing resulted in a huge like bank overdraft because they were like, the forecast looks good. We don't need any money. And then the money didn't come back and we had already paid out our customers. So things to keep in mind. Pandemics don't show up in holidays. But yeah, that's my talk. I hope it was fun.
Oh, that was great. Can we please give Ray a round of applause in the chat? Let me just paste my emojis. All right. Yeah, so we did have a few questions. Let's see. So the first one is about your makefile. So people do love your makefile. I think you might have had a talk about a makefile a little while ago.
I sure do.
Yeah. Do you have like a public makefile template for people to use?
I don't know if I do, but I do have my talk on makefiles. I can post that.
Cool. Yeah, so we will get that link shared both on the meetup as well as this YouTube. So again, we have another question from Michael. Michael, I just want to give a shout out for participating so much in tonight's event. We appreciate you. So for holidays, can they be one-off, or are they only one-off, or can they also be reoccurring?
Oh, they can totally be reoccurring. What's a good example? Like the day after Christmas, Boxing Day is like in Canada a big thing, and like is sometimes a thing in Australia. So for like some of our customers, it was really important, and some it was not. It was not part of like the default holidays that I got out of Prophet. So I just said, take Christmas and add one day, and then create that year over year. So like really when you're creating your custom holidays, you're giving it specific dates.
Okay, so it's like, so it's like using a generator to generate those dates?
Yep.
Awesome. Mm-hmm. Cool. So
part of my date calculator module actually does that. It you can say like create holidays for this specific region or this specific thing this far into the future.
Got it. Okay. And so when you're using Prophet, like how many periods do you need to have like effective predictions?
I tried to use 2 years of data. That didn't always work because some customers would just stop using us and then start back up 6 months later. Some would want to get predictions after a month of being on the platform. It's just kind of all over the place. I think honestly, it depends on how far forward you want to go. If you're trying to predict the next 30 days and you've only got 30 days of history, you can totally do it. It's just going to have a very wide confidence interval, meaning it's going to have a lot of uncertainty. It's also not going to know the seasonality from, years past from different months.
Yeah, that makes sense. So I actually had a question. Like you mentioned you're using PyTest. How do you think about testing this kind of like workflow?
How do I think about testing what?
Like, how do you think about testing like time series analysis? Like, what is like, are you just sort of like setting a seed and like assuming that information is coming? Like, I'm not too sure like how to ask the question. Like, I don't deal a lot with like data science, but it's like, how do you test time series analysis?
Really dumb tests. Did it give me a negative output? Not a good output, right? I don't know. Like basically like ways you can do it is like have kind of like a very dumb forecast, like just predict a straight line and then say like, well, how far off was it? How bad is the R squared, or like measure a fit? And then like have like a minimum threshold for that. I didn't do a lot of smart tests for actually on the predictive outputs because it is really hard and I didn't really want to think about it too much. Most of my tests were like unit tests on my functions. Like, is my math good? Is my date calculator thing working right? Is my connection to AWS like getting messed up?
Yeah, I mean, like those kind of like deterministic tests are like sort of what it's all about. I just to sort of plug our next talk, Sean was mentioning his project has 100% code coverage, so just gonna sort of see what that's all about too. But before we do let you go, do you have any like calls to action or words of wisdom for the ChiPy community?
Probably, but I can't remember because I'm not sleeping very much.
Okay, yeah, I mean, like you have a lot more on your mind, but like we do appreciate you taking your time out of your very, very busy schedule to give this talk. So thanks again. Can we please give Ray a round of applause in the chat? All right, Ray, thanks so much. We'll see you around. All right, so that was Ray Buhr talking about how to use Facebook Prophet in production. A lot of actual interesting information about like how to set up folders, like a little bit of the nitty gritty that you normally don't hear about. We're actually going to be taking a 5-minute break, but before we do that, if you're still here and you're enjoying tonight, go down below and hit that like button. It really helps us out. Also, we're really close to having 1,000 subscribers, so help us get over that, or help us get that milestone. If you have not subscribed, please do so. Actually, we'll be back in 5 minutes. Thank you. All right, and we're back. So thanks everybody for a very special episode of the Chicago Python live stream. Tonight's episode features time series analysis. We just had our first two speakers present. The first speaker was Anais Dotis-Georgiou. She was talking about InfluxDB and Facebook Prophet. Next up was Ray Buhr talking about his experience using Facebook Prophet in production. A lot of great tips on setting up projects and using makefiles. I absolutely love makefiles, so I just wanted to give that another shout out. We actually going to have our third presenter start. We have Sean Law. I'd like to welcome Sean onto the ChiPy live stream. Hey, Sean, how's it going?
Good. How are you, Ali?
I'm doing great. Thanks for being on. Can you please introduce yourself to the Chicago Python community?
Yeah, definitely. Sean Law, based out of Ann Arbor, Michigan, not too far from Chicago, right next to the University of Michigan here.
Go Wolverines.
So I am a data scientist, a senior data scientist working at a company called TD Ameritrade, so a financial firm. Maybe we'll get a little bit more into that later too.
Okay, awesome. So can you talk about like how did you first get into Python?
Yeah, actually, I resisted getting into Python when I first started. This was in 2005, or around 2000, yeah, about 2005 when it first got introduced. I was doing a summer research, so as a scientist prior to this, and just out of necessity, there's some software that I was using, some visualization software that I was using that used Python, so it was kind of thrust into that. But prior to that, I only knew like HTML.
Mm-hmm. Awesome. And so like, so what are like some other things? Like, I know you're doing a lot of time series analysis. Like, how else do you use Python?
Yeah. So part of my regular job at TD Ameritrade, a large part of it emphasizes the use of like the PyData stack. So whether it's using visualization tools, which you'll see later, such as like Bokeh, Seaborn, Matplotlib, or just number crunching, numerical computing, using things like Numba, NumPy, SciPy. And then all of your statistics packages, right? Like, and also machine learning. So scikit-learn, stats model. So it sort of runs the gamut. My day-to-day changes all the time, whether you're hopping in and out of Jupyter Notebooks or even VS Code, or trying to figure out how to exit Vim, right?
Yeah, exactly. Right. It's I'm still think I'm getting there, but yeah, it sounds very exciting. Like trying to do different things like every day. So like our community members have like not really been able to meet in person. We've been doing a lot of virtual events sort of keep that connection going. I know you're also an organizer of the PyData meetup in Ann Arbor. So how have you all been dealing with COVID-19?
I think for now, so we've been on pause. Also because PyData is affiliated with the TD Ameritrade, and we were previously being hosted on site in our office. And so a lot of that stuff was obviously paused. But now we're thinking about how we might engage virtually, very similar to what you're doing here, Ali. I think it is a great example of a successful online meetup now.
Yeah, thanks for saying that. Yeah, if you need any help, please feel free to ping me. We'll love to get you started. So are you ready to go with your talk?
Yeah.
Let's get your screen shared and we can just get it on the broadcast. Perfect. Sean Law, the floor is yours.
Great. So I'm really excited to be here today to tell everybody a little bit more about modern time series analysis with a fairly new package in the data science space called STUMPY. For those of you who want to follow me on Twitter, you can find me at Sean My Law. As well, if you want to follow the development of STUMPY, you can also follow us at Stumpy_dev. So,
Sean, before, do you mind just hitting that button to like hide that?
Yes, absolutely.
Oh. Sorry for interrupting.
No problem. Here we go.
Awesome, thank you.
Cool. So just as a reminder, we'll have a couple of pausing points throughout the talk. So be sure to ask your questions in the chat, and then I'll have Ollie relay them to me. So just so I don't forget to acknowledge the folks that really matter here that have done a lot of this work. So I want to acknowledge two research groups, one over at the University of California, Riverside, the PI there, Iman Kio, as well as at the University of New Mexico, Abdullah Muin. These are really the researchers that have produced and published a lot of these papers that are related to what you're about to see today. And STUMPY really basically just takes a lot of those ideas and sort of packages it into a very easy to use, user-friendly Python package. Also, obviously, I'd like to thank Ollie at ChiPy for inviting me to here to give a talk. As well, I'd like to thank TD Ameritrade, my employer, for giving me this chance to share this work with you. For those of you who aren't really familiar with TD Ameritrade, we're a financial trading firm. So whether you're a long-term investor, like a retail investor, or you're an options trader where you're trading futures, foreign exchanges, or just day trading, or maybe you're a financial advisor, we really offer a large amount of sort of fantastic platforms for investing, as well as great educational content. A few months ago, TD Ameritrade was actually made it onto the Fortune 500s list. So we're very, very proud of that. Now, as a company, our company purpose is to transform lives and investing for the better. And really the emphasis starts with transforming lives. One of the ways, as Ollie mentioned, that we are helping to affect our community here in Ann Arbor is I'm one of the co-organizers of PyData Ann Arbor, along with Ben Zeitlin from NVIDIA, as well as Rose Putler from Duo Security. We've been doing this for a few years now. Check out all of our videos on YouTube. As well, a call for action here is the PyData sort of parent group is organizing a PyData Global with all of the local chapters across the world. And the call for proposals ends on August 2nd, so make sure you participate and submit a proposal for a talk. Just a little bit about me. I work on a team called the Exploration Lab as a senior research scientist and data scientist. And so on the Exploration Lab, our goal is to explore new and emerging technologies or methodologies that might help the company differentiate itself from our competitors. And STUMPY is one of these technologies that was first incubated in this group. So whether you're a data scientist, an academic, or maybe you're just like you're a analyst or a researcher, or maybe you're a software developer, engineer, or maybe you're managing a data science team, or perhaps similar to some of the people who are on this meetup right now, you're just a curious learner. Hopefully there will be something here for you. This talk is broken up into two parts. The first part is really to cover sort of the background and all the motivation. And then the second part, we'll get into live demos and a little bit of a review. So here's the problem. So we're talking about time series today. Here's the core of the problem. I'm sure everybody's been there before, where either you have some business team or a technology team, or maybe you're just collecting data, and this large amount of data lands on your lap. So in this particular case, somebody says, "Hey, here's some data. Now perform some magic, Dr. McFancy Pants. You've got a math degree or an advanced degree. Show me something interesting." And maybe you're lucky and you have a small data set where there's 10 data points, and you can visualize it very nicely and maybe pull out some quick insights from that. Maybe your data has 100 data points. It gets a little bit more complicated, but visualization is still possible. What if your data points get to about 1,000 data points? Now visual comparison of these data points becomes excessively hard. And then if you get to about 10,000 data points, forget about visualizing it, right? You really need to apply different analytics techniques in order to start analyzing this data. And once we get to things that are even beyond 10,000 data points, we've all sort of been there. We get this overwhelming sense of dread. And you could just think that you wish that you had a magic wand where you can just wave it and maybe wish it all away. Or at least maybe you could wave some other magic wand that could at least tell you where you should focus your attention, right, when looking at your time series. And what are some of the classic ways that people might analyze their time series data? We talked about visualization, but obviously once it gets a little bit larger, it's impossible to use. You might reach for our good friends stats, right, where you might analyze, let's say, the mean or the median or some other global statistics like the max or the min. But very rarely when you're analyzing time series data, do you actually care about these sort of single point statistics, right? What you really care about are maybe a subsequence or a context of continuous parts of your time series, and being able to extract meaningful information from that. Some folks might apply something called an ARIMA model, where you're basically building an autoregressive model. But this also assumes that that there's sort of a repeating pattern in your data, but not all data necessarily has repeating patterns. Or you might do some sort of anomaly detection, finding points along your time series that might be anomalous. Now, the problem with anomaly detection is that you first have to define what an anomaly is before you can detect it. Now, anomaly you might define as maybe a single point. But what if you see that point a second time? Is it still anomalous, or is it now normal, so to speak? So that's really a fuzzy gray area. And of course, we had 2 wonderful talks just right before this about time series forecasting. So leveraging tools such as Facebook Prophet is a great idea. But this also assumes that you have either enough data or that you trust your historical data to give you reasonably good predictions of the future. And of course, everybody's favorite thing to do is, why don't we just throw more data at the problem, right? Or if you're really trusting every data, you might think about clustering these time series. But this really gets into an area where it becomes computationally expensive. And there's something that's very, very popular called dynamic time warping, where you take different time series and you stretch and compress those time series and see if they are similar to each other. And then last but not least, in the age of artificial intelligence, deep learning, everybody's favorite hammer looking for a nail to hit, right? But regardless of which method you choose to analyze your time series data, there's sort of one key point here, right? Which is that there's no silver bullet. Each time you choose a particular analysis method, you're looking at some sort of trade-off, obviously. And maybe just for the record, right? While I've studied time series for a good part of my life, I'm by no means an expert. Even still today, I'm learning tons from other folks. But really, what is the goal? So let's think about this. Let's simplify this a little bit. What is the goal of time series analysis? And to sort of answer this question, let's take a simple illustrative example. So here's a very, very simple time series that has 13 data points in it. So n is equal to 13. Now, as we mentioned before, we can maybe visualize it and look for maybe identify interesting points. But really, we want to look at maybe parts of the time series that may be repeating itself, let's say. Now, how might we analyze this time series? Now, to answer this question, being sort of a reformed scientist, so to speak, I like to pose this question to everybody who's on this this presentation right now. So who is this person that you're staring at right now? Any guesses? Well, actually, you might know this person as William of Ockham. And he's actually best known for something called the law of parsimony. Or in modern science, we just simply call this Occam's razor. And Occam's razor states that simpler solutions are more likely to be correct than complex ones. So let's think about that for a second. Simpler solutions are more likely to be correct than complex ones. And so thinking more about what do we really want to do when we're analyzing our time series, we really should be answering this question, right? Which is, what is the most simple and intuitive approach that we can take in order to analyze our data? So how do we strip away that complexity? And hopefully some of the sort of key qualities of this approach might mean that the approach is easy to interpret. So it doesn't require you to perform tons of mental gymnastics in order to understand it. You should be able to look at it and interpret the results fairly quickly. Another quality is applying minimal assumptions. A lot of the times with the different methods that you're seeing today, especially in, let's say, machine learning, or even in statistics, right? It requires some level of assumptions. Can we strip away as many of the assumptions as possible in the approach that we're trying to take? Also, it would be great if the approach could be parameter-free. Going back to the machine learning examples, right? And thinking about hyperparameter tuning, or thinking about deep learning models where there's oftentimes millions, if not billions, of parameters to fit. If we can simply, use an approach that maybe has no parameters or as close to that as possible, that would be fantastic. And then another great quality is to not have any prior knowledge, right? Because maybe it's a new data set, we don't know anything about it, or maybe we don't have time to train a machine learning model. So if we can leverage an approach that doesn't require any prior knowledge, then this sort of satisfies the constraints of having something that's simple and intuitive, right, and easy to interpret, and that isn't a black box. So going back to our illustrative example, maybe we should start with a definition. So we know that this is our time series. I like to start with a subsequence. So whenever you hear me say the word subsequence, all this means is that I'm referring to a part or section of the full time series. So I'm not referring to the entire time series, just a small part of it. So here's what I mean. So this is our full time series. This green rectangle over here denotes 2 points, and this can be a subsequence of length 2. Similarly, this is another subsequence of length 3, and your subsequence could be as long as, let's say, of length 8. So all of these are considered subsequences. So now that we understand what subsequence means, then we can say, let's choose a subsequence length, m. So in this particular case, we're choosing the subsequence with length m equals to 4, right? Now that we understand what m is, how do we compare subsequences? Let's say, how do I compare this green subsequence with, let's say, this one over here on the right, shown in blue? How might we compare them? So to do this, one of the most intuitive and simple approaches to compare them is to compute something called a Euclidean distance. And the definition of a Euclidean distance is the straight line distance between 2 points. So what does this mean? So let's take these, let's simplify this a little bit. Maybe instead of taking 4 points, let's look at something that is a subsequence length of 2. So if I simply plotted these 2 points, 0, 1 is down here in the bottom left, and 1, 2 is in the upper right. These are just 2 points. And we said that in the definition that the Euclidean distance is simply the straight line distance between these 2 points. Now let's not call it some fancy name. Let's just give it a letter H to represent it. If I wanted to calculate the straight line distance between them, we all sort of know how to do this intuitively with very basic math. So we can draw a triangle, and we know that if we have a right angle triangle, we can compute h by seeing that h squared is equal to a squared plus b squared. We take the square root of both sides, and now we have the Euclidean distance. And this isn't anything fancy. I'm sure everybody recognizes this, masquerading as everybody's favorite Pythagorean theorem. So it's pretty straightforward. Now we sort of intuitively understand how might we compare these subsequences. And so we can plug in our numbers, and we find that the distance between these 2 short subsequences is √2. Now let's kick it up a notch, and let's increase the length of our subsequence. So notice here that we have added 2 new points to our subsequence, so it's of length 3. And now we modify our Pythagorean theorem by just adding the c² term. That's all there is. And we plug in our numbers in very much the same way with an extra term at the end in our summation. And we find that our distance, or the Euclidean distance between these 2 subsequences, is just simply √3. And now if I add a 4th term here, which gets us back to where we started in the first place, we see that we have a d² term, and we can quickly compute that the Euclidean distance between these 2 subsequences is square root 67. So not too hard. So obviously, as you add more terms, or elements to your subsequence, there are more terms in your summation. Okay. So I'll pause. Ollie, were there any questions in the chat?
No questions right now.
Awesome. But if you do have any questions, feel free to throw them in the chat.
Okay.
Thank you.
Thank you.
So now that we've defined how we compare 2 subsequences, we might want to then think about how do we compute something called pairwise Euclidean distances. So not only do I want to compare 2 of them, but let's say I wanted to repeat my time series down here in the bottom, and I want to take this reference subsequence and I want to compare it to the entire time series down here, maybe through some sliding window. And I'll record the distances in this vector down here. And this vector down here is just known as the distance profile. So if we simply say, I want to compare this green rectangle with this blue rectangle, I know how to compute it using the Euclidean distance. And because they're the same, the distance is 0. That's pretty obvious. Now I can slide this blue box over by 1, compute the distance again, slide it over, compute the distance, and just kind of keep going all the way across. And basically, I'm comparing the green box to the blue box. And then eventually, I run out of subsequences to compute, and we get our distance profile. And this is what I mean by pairwise Euclidean distances. Now, once I do this, I can start examining this distance profile and asking, is there anything interesting here? So the first thing you can do is say, well, which subsequence along this time series is most similar to this green box? Now, the most obvious one is obviously what is called the trivial match or the self-match. Obviously, you can match yourself. So this isn't particularly interesting. So usually we'll blank this one out, and then what we'll do is we'll scan across the remainder of the time series, or remainder of the distance profile, and look for the next smallest distance, which happens to be over here. So the closest match to this green subsequence is this blue one here, and they are separated by a Euclidean distance of 6.9. So we can continue this further. So this is just sort of one set of pairwise Euclidean distances. So what we do next is we can now take our reference window, this green box, slide it over by a single element, and we can just basically perform the same thing. Let's compute the Euclidean distance between this green box and this blue box. And we keep on sliding it across, computing every single pairwise distance, right? and really get a sense of how each of these subsequences match up. And again, we can find the closest one to this green one, and that's all the way down here, right? And it actually has a distance of 1.4. And you can see that these two sequences or subsequences are pretty close together. Now we'll repeat this, obviously, by moving our green box over. And as you can see, we could just keep doing this ad nauseum until our green reference box ends. And we end up with many, many different distance profiles. And if we start stacking these distance profiles, one on top of each other, we get something called the distance matrix, which is shown here. So each row here corresponds to one of those vectors that we had seen earlier, right? And all of these green boxes just denote the distance to its nearest neighbor for a given subsequence. Now, if you think about this distance matrix, right? All of this stuff seems pretty intuitive. We know how to compare our time series sort of with respect to itself, or perhaps with respect to another time series. And it's, again, very easy to interpret the meaning, right? We don't have to think about, well, what does a Euclidean distance mean? It's pretty straightforward. It's just a straight line distance. And we really haven't made any assumptions in the sense that this is generally applicable to any time series. It's not specific to, let's say, finance or any other particular area. And thinking about something that's parameter-free, realistically, we haven't really chosen any parameters. Maybe you could argue that the subsequence length, m, is a parameter, but that's just one parameter. And again, the great thing is that we don't have to do any model training. So there's no real prior knowledge that's required here. And so it really, this approach of computing these sort of pairwise Euclidean distances really satisfy our need, right, of finding something simple and intuitive. And so the next question that we would ask is the solution, is this particular solution scalable? Okay, because if we're thinking about, a simple toy data set, maybe it works well, but does it scale to larger and larger data sets? So if we think about how we might, build up this entire distance matrix, the brute force calculation actually can be done in a few lines of Python code. So in the top here, I'll draw your attention, is n equals 13 is just simply the length of our time series. M equals 14 is just the subsequence length that we chose. And this is our time series that we were showing before of 13 data points. But really, to actually now compute the pairwise Euclidean distances for this distance matrix, it's embodied in 3 for loops. This outer first for loop controls the green subsequence that slides across. This J for loop controls the blue subsequence sliding across our time series. And then our innermost for loop here, K, actually computes the pairwise Euclidean distance for each of the elements within a given subsequence. So we have a triply nested for loop. And for those of you who are savvy with this type of stuff, this actually gives you a computational complexity of O of n squared by m. And also, if we were to sort of store this entire matrix, this distance matrix in memory, it would require a space complexity of O of n squared, which is typically not what you want to do. And to really drive home the point here, why don't we take an example of a brute force calculation of every time series that's actually larger. So there's sort of a back of the envelope calculation here. So imagine you had some sort of IoT device where maybe you're collecting data every 3 seconds. So that means that you're collecting data 20 times per minute, and maybe you're doing this 60 minutes an hour, 24 hours a day, 365 days a year for 5 years. So that means that for 5 years straight, you're collecting data every 3 seconds from some sensor. This would actually produce just over 50 million data points in your data set. And if you were to take this brute force approach and to compute this distance matrix, all these pairwise Euclidean distances, it would actually take you just over 4.4 years to compute. And not even to mention that the memory requirements is 11.1 petabytes of memory just to store that into memory. So if we go back and ask the question, is this solution scalable? Unfortunately not. But at the same time, we now understand why. Even though there's a very obvious and straightforward and intuitive approach to analyze your time series data, since it wasn't scalable, that explains why these methods that you're seeing on screen here have become so popular, right? Because they do work and scale well to large data sets. Well, that is until now. So as I mentioned at the very, very beginning of this talk, a group of researchers at the University of California, Riverside and University of New Mexico actually published a series of back-to-back papers at around sort of November, December of 2016. And this paper outlines something called a matrix profile. And so when I saw this, it seemed quite interesting. It was related to these distance matrices. So what is a matrix profile? So the definition of a matrix profile is a vector that stores the distance between each subsequence within a time series and its nearest neighbor. So given, let's say, one of those green subsequences, you're only storing the distance to its nearest neighbor. So conceptually, what this means is that given the distance matrix on the left here, all we're doing is taking those green boxes, which denotes the distance to its nearest neighbor for a given subsequence, and we pull them out. And we store only this information in a single vector. So this means that instead of storing the full n squared distance matrix, we just simply store a vector that is of length n. And now these researchers then went on to also claim that not only is it sufficient to just store this matrix profile, but that they could actually do this exactly in O of n squared computational complexity time, right? And that sounds sometimes too good to be true. But let's just set that aside. So given this matrix profile, let's say for this particular time series, this is the matrix profile for it. What can we do with this matrix profile? So the first thing you can do is you can plot it and use it to annotate your original time series. So we'll plot that here. And so when we look at it, we'll observe a couple of things. We'll see that it sort of goes down and then back up, right? And then down again. So we see some minima over here, maybe potentially some maxima over here. Now, if we actually explore those global minima, there's two of them, right? These two right here with a distance of 1.4. And we're aligning our matrix profile with our original time series. So these distances actually correspond to the one on the left corresponds to this subsequence, and the one on the right corresponds to this subsequence. And it just so happens that this is often called, this global minima is called a motif. So these two subsequences happen to be very, very close to each other. Because if you look at it, the very first point are the same. The second point are off by 1. The next point is the same. And the last point here, 9 and 10, are just off by 1. And so you understand conceptually why these are perhaps a good match. And this is a potential pattern within your time series. So whenever you have a motif, that is an opportunity to identify something as a pattern. Now we can take this a step further, right? And or the researchers took this a step further and said, not only should you be aware of something called the matrix profile, but there's something also called the matrix profile index. So the index, which is the index location of the nearest neighbor for a given subsequence. So going back to our example here, the subsequence on the left has a nearest neighbor that is a distance of 1.4 away from it. And it just so happens that that nearest neighbor, the subsequence of it, starts at index 8. So this is 8 here. All we got to do is come up here and find index 8 and find that this subsequence is this one's nearest neighbor. Similarly, this one over here, this blue one, also its nearest neighbor is at index 1, and so it's pointing up here. Now, just to drive home this point here, and obviously every other subsequence within this time series also has a nearest neighbor. To further interpret this, what if I took, let's say, this subsequence over here? To find out where its nearest neighbor is, we just come down to our matrix profile, which is aligned with our time series. And we see that it's this green subsequence's nearest neighbor starts at index 2 and with the same length. And so we just come up here to index 2 and we find that this is its nearest neighbor. And these two subsequences simply have a distance of 6.2. So we can quickly interpret what the meaning of this matrix profile is very quickly. Now we can do something else. So instead of looking at global minima, we can also look at the maxima. So if we scan across our matrix profile, we see that the largest value is 14.1. And this corresponds to this particular subsequence. And what this is telling you is that this particular subsequence doesn't actually have any other subsequence that looks like it. In fact, it looks so different from it that it has a distance of 14.1. And so what this is suggesting is that this subsequence is a potential discord, or it is a discord, but that it is also a potential anomaly within your time series. So think about this. If you're able to compute your matrix profile, you essentially get patterns searching or pattern matching for free, as well as potential anomalies for free. Now, we talked about the fact that the brute force method had a pretty nasty computational complexity as well as space complexity. And these researchers at the various institutes published a series of papers. In the first paper, the algorithm was called STUMPY, which leveraged a fast Fourier transform to shave off some of that computational complexity, so it became O of n squared log n. They then published another paper where they introduced an algorithm called STOMP that does the same calculation, but instead of computing this full matrix profile in n squared log n, it does it in n squared time. And then this was performed on CPUs. Then they thought about, well, what if we throw better hardware at it? And so they produced something called GPU Stomp. So they migrated this Stomp code over and applied it onto GPUs and found basically that it could be really, really fast. And in fact, in their published work, they demonstrated that they could compute for a time series of length 100 million, right, which is twice the amount that we had shown for that brute force calculation. They could use their implementation called GPU Stomp, which is using 2 GPUs, and they could compute the full matrix profile in just over 12 days. All right, and if you think about this is basically like taking 10 years worth of data, right, and computing this in 12 days, which is faster than real time, so to speak. And if you were to do this in the brute force way, you'll see that it takes about actually 1,600 years to compute. So you don't want to be doing this the brute force way. And even this is Eamon Keogh. He is one of the primary investigators of this matrix profile work, and he said that given the matrix profile, most time series data mining problems are trivial or easy to solve in a few lines of code. And he also later went on to say that these are the best ideas in time series data mining in the last 2 decades. And in my opinion, anybody who says this has to be a real gangster. But being a scientist myself, I like to think that extraordinary claims require extraordinary evidence. And this was stated by the late Carl Sagan. And so this is where our journey at TD Ameritrade started, which is we decided to, from this published work, we thought, how could we actually try validating some of these claims of being able to not only compute the matrix profile, but to be able to do it in a short period of time. And so based on their published papers, we tried implementing it. So we tried validating it. So we used core Python, and for the numerical computing components, we tried NumPy. And the first thing that we did was, so we actually didn't look at the full 100 million length time series. We just took something pretty modest. So this is about 2 million data points in length. And in their published work, using their GPU Stomp algorithm, they demonstrated that they could compute the matrix profile in 9 minutes. So I implemented the same thing, right? And on a single CPU, it just took way too long. It doesn't even register. It was more than 300 minutes. It was way, way too long. And this made me a sad panda. But then I started thinking about, well, what if we tried to parallelize the code? Maybe using multiple CPUs, not just using a single core. Well, then I started looking at using something called Numba. So Numba is open source software that is really a great tool. So for those of you who are maybe more familiar with using things like Python, Numba basically allows you to write Python code, and it JIT compiles that code for you. And not only does it do that, but it also automatically parallelizes that code for all of the CPUs that are on your particular server. And so we applied Numba to 16 CPUs, and we were able to see that we were able to actually compute this matrix profile for 2 million elements in about 3 hours. But something to note here, right, is that we moved from a single CPU to 16 CPUs in 2 days. So I know a lot of people like to give Python a hard time, but we think about this. We were able to move to multi-CPUs in a very, very short period of time. So if you're interested in parallelizing your code, I would highly recommend using Numba. Then we thought, well, what else can we do? If we think about the algorithms that were published and think about the brute force method, there's really a space that we realized was missing from just looking at a single or parallelized CPU code from looking at GPU code, and something in the middle, which is, what about thinking about multi-core distributed, right? And that's when we decided that we were going to leverage the right tool for the right job. In this particular case, we looked at Dask, and specifically Dask distributed, where we can distribute our code across multiple servers now, and then parallelize across each individual server. And now we were then able to scale up to 128 CPUs, right? And that brought our computational time down to 13 minutes. And remember this, we started with pure Python or NumPy code, and we were able to now distribute across 128 CPUs in a matter of 7 days. Within a week, we went from single CPU to distributed multi-core CPUs, which is a testament to the development of these open source tools and why we need more of them and why you should use them as well. And so now that we know that we can distribute it that now we understand it's scalable, we sort of went back to the original publication that looked at a time series that was 100 million data points long. And if you recall, this GPU Stomp, it was able to compute this in just 12 days. And now using our implementation, now with 256 CPUs, we were actually able to compute this matrix profile in just under 10 days. And now, just to be clear, we're not saying that CPUs are faster than GPUs, because that would not be a smart thing to say. But what we're saying is that Python code on CPUs is actually quite scalable. So you can get there very, very quickly. When we scaled to 256 CPUs, we didn't actually have to change your code. We just had to spin up our extra servers and then run the code, and it was essentially complete. So going back to our original question, is the solution scalable in terms of computing this matrix profile? Absolutely scalable. So we can now start thinking about how to analyze our data. Our version of this algorithm, this sort of distributed parallelized version of our algorithm, we call it STUMP. So it's kind of a play on words of the published algorithms of STAMP and STOMP. The U sort of pays homage to the fact that we're using Numba and NumPy sort of in the numerical computing world, but also because Ann Arbor, Michigan is often known as sort of tree town or tree city United States. And so we aptly named our algorithm STUMP. Now you might also notice that we have stumped with an ED at the end. If you're looking to use that algorithm, that is actually our distributed algorithm. So STUMP is for sort of on a single server. Stumped is for multi-server computation. So you can compute your matrix profile on a single server or multiple servers. And just so we can kind of visually see what that performance looks like, here is this benchmark. So this is this GPU Stomp, this published work, right? These are some of the few data points that they demonstrated. And again, this is using 2 GPUs. And what I'm going to lay on top of this is our CPU. So this dotted line up front here is using 2 CPUs, 16 for this one. And this line out here is using 128 CPUs. And you can even see here, this 256 CPUs is doing nearly as well as the GPU version. So it scales out pretty nicely. And so now we're at May of 2019, so just about a year ago, where we sort of wrapped up this work. And we decided at TD Ameritrade that we were going to open source this and share this with the data science world and share this with the public as part of our effort to transform lives for the better. And this is where STUMPY comes into play. So STUMPY is a powerful and scalable Python library that efficiently computes this matrix profile. And once you have this matrix profile, you can use this for a variety of time series data mining tasks. And we'll get into more of that in our live demo later. When we first released this last year as a version 1.0, we had full unit test suite with 100% code coverage and minimal dependencies. Oftentimes you get these data science packages that are very dependency heavy. We only rely on NumPy, ChiPy, and Numba. And then if you want to do the distributed version, then there's a soft dependency on Dask. But it is compatible with Python 3.6, and you can conda install it through the conda forge channel, as well as pip install. And obviously, you can find our code on GitHub. Here's a short version of the URL at tiny.cc/stumpy-code. So go check it out there. I'll post this at the end of our talk as well. And then with that, I'll pause for questions before we get to the second part of our talk, which is the live demos, the most fun part. Ollie, were there any questions?
We just had a question come in from Paul. What can you do with the resulting computation? How is this information visualized?
Perfect. I think we'll hold that question because we're right about to get into the live demo. How about that?
All right, let's just jump right in.
Okay, so just maybe to keep you a little bit more suspense, just a quick year in review. So again, Stumpy was released in May of 2019, and we're now in July of 2020. And so obviously we celebrated our Stumpy's first birthday, which we're pretty excited about. And since that time, we've had tremendous growth, around 36,000 downloads and installs, and constantly increasing. We have a ton of great documentation and tutorials, which I'll outline, which I'll show and point you to later. But just to kind of show you that people are looking at our documentation throughout the day, and not only that, but also throughout the entire world, whether it's in India, Australia, even folks in South Africa are really using Stumpy and reading our documentation. And also, we have just over 1,300 GitHub stars. So thank you to all of the people who gave us a star. And now we're at version 1.4.0 since our humble beginnings of version 1. And there were some things that a lot of new features that we've added since then. The first and most important thing is sort of what I call sort of the need for speed. We obviously did a lot of CPU work, but we also thought that, well, what are our friends that are not that are doing deep learning? What should they be doing when their GPUs are idle? Well, we thought, well, could we take this, Stumpy code and port it over to GPUs? And maybe how might we create something called GPU stump? Right? Obviously, the published work did something like this. Could we follow in their footsteps? But in order to do this, we had to think about, well, how do we incorporate and sort of access GPUs? For those that are doing deep learning, you're probably familiar with PyTorch coming out of Facebook, or even TensorFlow from Google. A lot of these APIs for doing deep learning or computing on GPUs tend to be changing very rapidly. There's also a new kid on the block called QP or ChiPy, which is meant to be a drop-in replacement for NumPy. So check it out if that's your cup of tea. Or some people actually write raw CUDA kernels or raw CUDA code and then wrap it in Python, right? But a lot of times with sort of these packages constantly evolving, right? It's somewhat hard to keep up. But as a maintainer of Stumpy, one of the things that I really wanted to try to avoid was any additional dependencies. We really appreciate the fact that you can, as a user, download and install Stumpy. Hopefully, within 30 seconds of doing that, you can run and analyze your data. But if there were additional dependencies, this becomes harder. And I kind of think about it as you're drawn into dependency hell. And so it turned out that really the right tool for the right job wasn't any of the packages that I talked about earlier, but instead, the right tool for the right job was Numba. So not only does Numba allow you to parallelize your code, but Numba also has GPU support and allows you to allows you to JIT compile your code directly to CUDA code, which is phenomenal. Now, obviously, there's got to be a catch, right? So what's the catch? So there's a couple of pros and cons for those of you who want to do this type of work. The really great thing is that, again, no additional dependencies, which is a plus, right? If you're already using Numba. But you do have to maintain a separate code base that targets a GPU. So you can't just take your straight Python Numba code and then say put it on GPUs. You still have to write it differently. But the good thing is that you're still writing Python code, which I love. Now, having said that, there is, and this isn't necessarily a Numba problem. This is more of a GPU issue, which is you have to think about multi-threading, this multi-threading paradigm in GPUs, which is fundamentally different from the way that you would code for CPUs. But once you sort of wrap your head around that, then everything becomes smooth sailing. And another great thing is that you write Python code and it automatically compiles to CUDA. So you don't actually have to keep CUDA code with your package. All of that's handled for you. And you don't have to compile any of it or stuff it into your Python packages. Now, there is one con, which is if you're using Numba, you might have a delay in the CUDA functionality. So if new CUDA functionality comes out, it might not immediately get added to Numba quickly. But Numba also has excellent host-to-device APIs for moving data from your host, which is your CPU side, to your device, which is your GPUs. But to also keep in mind that with using GPUs, there could be memory limitations. So a lot of times if you're using commodity GPUs, you might be limited to, let's say, 11 to 12 gigs of GPU memory. So you should keep that in mind. But again, out of the box, using Numba, you can actually leverage multiple GPUs if you have multiple GPUs on the same server. And then last but not least, this is probably the most challenging bit if you're open sourcing your packages, is writing unit tests for Numba GPU code, and then also continuous integration for GPU code is quite complex, especially when you have a package like STUMPY that tries to maintain 100% code coverage. But we can discuss that maybe in the Q&A if you're interested. So taking a look, obviously we were able to successfully do this and port our code over to GPU, and we created something called GPU Stump. And this is, again, the CPU is shown in purple. The yellow is really that published benchmark. And what I'm going to show you in blue here is the dotted blue, the dashed blue line is our GPU Stump analysis, or creating our matrix profile using a single GPU, right, which isn't bad at all. And then with 2 GPUs, it basically performs nearly as well as the benchmark. And thanks to our friends over at NVIDIA, shout out to Ben Zaitlin, as well as Josh Patterson over there, we actually ran STUMPY on their DGX1 and DGX2 GPU cluster, which has 8 and 16 GPUs on the same server. And you can see that STUMPY actually scales out almost linearly, all the way out to just over 130 million data points. And mind you, we didn't have to change a single line of code. We just installed the STUMPY code onto that server, and we just ran it without any issues. So it really is a testament to how great the software Numba is. So now that we've shown this, I'm sure everybody's thinking, well, in order to run it on GPUs, it must be a bit of a change in the code. Turns out, this is what it looks like. So imagine you have a time series that looks like this. This is just a simple example using 10,000 data points. Then your subsequence length is 50. The CPU version of the code just looks like this. You just call STUMPY, stump, or the stump function, and then you hand it the time series as well as the subsequence length. And if you wanted to do this on GPUs, this is the GPU code. Notice here that the difference between the CPU code and the GPU code, assuming you have a GPU on that server, is just 4 characters. So you don't really have to change much. You can test it on the CPU and then move it over to GPU without much hassle at all. I'm sure that a lot of you are thinking, can has a GPU as well? I'm on your side, and it turns out that you can have a GPU as well. So there's something called a Colab. So for those who aren't so familiar, the Google Colab in my brain is sort of Google Drive meets Jupyter Notebook. So this is Google Colab is from Google, and so there's a link down here. So if you go to tiny.cc stumpy_colab, right, you'll be able to access this example STUMPY notebook that actually walks you through how you might run STUMPY on GPU. And actually, Google Colab offers you a GPU to use for, I think, for 12 hours, if I'm not mistaken. So go check out this notebook. And again, I'll post this slide at the end here, or this link at the end. So now that we have GPU Stump, so we've scaled across to GPU devices, we've also added something called M-Stump. So the M standing for multi-dimensional stump. So the multi-dimensional component of this is if you have multi-dimensional time series. So then maybe instead of having a single, let's say, sensor collecting data, you might have 10, 20 sensors collecting data at the same time. Maybe you're collecting temperature, pressure, and so on and so forth. You can actually analyze all of these time series together as one. And so there's also a distributed version called M-Stump. Also, we have an approximate version of the code called Scrum. So where you can compute an approximate matrix profile without committing a full large amount of time computing the full thing. You can actually get a pretty good approximation of it using this algorithm. And if you're looking for streaming data support, we also have that too now in STUMPY. And so I'm going to move into the live demos, and I'll switch over to our browser over here. So this is our code on GitHub. So check us out, or you can just search for STUMPY Python. Here's the notebook, the Google Colab that I just mentioned. So in just a few lines of code, you have access. It shows you how to install STUMPY on that Google Colab notebook, how to import the package, and then finally how to execute the STUMPY code on CPU and then also on GPUs, and a few short lines of code. But here's really where the fun begins. So here is an example. So I want to draw everybody's attention to the very top here. So this is a time series at the very top, right? I want everybody to take a look. Can you spot anything interesting coming from this time series? Are there any repeating patterns? Maybe there is, maybe there isn't. Can you spot any outliers, any anomalies, right, in this time series? Now, not to belabor the point here, but even what if I showed you that this is actually the pattern that you're looking for? Again, hindsight is 20/20. So your data, with your original data, you won't know this, obviously. But what if I showed you this pattern, and I've zoomed in green here? So I've blown it up, and you can see it in green. Can you spot where along this time series does this pattern repeat itself? And it turns out what matches this particular time series, or what matches this particular pattern, exists all the way in gray on the other side. And I've also overlaid this gray line on top of it. And you can sort of see exactly why this gray subsequence matches the green subsequence. And this number here, this 5.5, is that Euclidean distance that we talked about. So it's not 0, because there are some differences between these two subsequences, and those differences can be attributed maybe to this section over here and a little bit over here. But for all intents and purposes, you probably agree that these two subsequences are a match towards each other. And what we're showing you here is that matrix profile, right, for every single sliding window of this green subsequence that moves across. So you can see that the global minima is located right over here and right over here. So where the green and the gray boxes sort of are aligned right on top of it. And now that explains that the global minima actually give you that motif and give you a very strong pattern match. But because we have all of the pairwise distances, when I press play here, it will basically slide that green subsequence, this sort of reference window, from left to right, and you'll see this gray box jump, right? Because it actually spots where that closest pattern is. So I'll play that for you, and you'll see, right? Now, one thing to point out, too, is that wherever your reference window is, this green box, what matches that pattern doesn't always have to occur in the future. It can also occur in the past as well. So that's why you see this gray box behind it. Right? So there's something to keep in mind. And going back to what we were saying about looking for potential anomalies. So to do that, you basically go to your time series, your matrix profile, and you look for the maxima. In this particular case, that's this green subsequence right here. And you can actually see that the closest match to this green subsequence is this gray subsequence. And it actually has a distance of about 22.3, which is a very, very far distance away. You can tell why, right? They're not actually that great of a match. There's huge differences over here and differences all the way over here as well. So just by computing the matrix profile, all you need to do is just look at your all you need to do is just look at this matrix profile, look for the minima, and you might have multiple minima or local minima along the way. And you can also analyze the maxima as well. Now, there are a couple of other things that you can do with this matrix profile. I recommend everybody go to the STUMPY Read the Docs documentation. In our tutorials, we have wonderful, very full-length tutorials, very verbose, that actually tries to take the original publications and reproduces a lot of the figures from those papers and elaborates on some of those concepts. But a couple of things that I think are quite exciting, that once you compute that matrix profile, what can you do with it in addition? So one of these things is you can look at something called time series chains. And what is a time series chain? So if you can imagine this plot here where each data point might be a subsequence, right? And if you have points that are close together, it just signifies that you have subsequences that are close together, in Euclidean distance. Now you could have subsequences that are just clustered randomly but very close to each other. But you can also have subsequences that are close to each other, but that that are different along some sort of directionality, along some direction. And here's what I mean by this. So if we kind of scroll down here and we look at this particular time series. So this time series is search queries for the Kohl's department store, shopping store. And this is just showing you how many, I think, Google web searches that people have been querying since 2004. So we see, year over year, right, obviously there's an upward trend, but also what we're noticing is this little hump here, sort of near the end of the year. And maybe I'll have you kind of do a little thought experiment of what does that hump represent? And the point here is that if you take this time series, this raw time series, and compute the matrix profile, what you can extract out of this are the minima, which are your motifs. But then you can actually take this matrix profile and compute the time series chains. And what it will do is it will highlight for you from this time series a pattern that's not only repeats itself over time, but that is sort of monotonically moving in a certain direction. So you can see that the time series chains computed from the matrix profile, right, has extracted these particular humps along the way. Again, somewhere near the November and December timeframe. And there's two things to note here, right? In this particular pattern in 2004, it was just one straight hump. And then in 2005, you start to see what looks like this sort of bimodal hump. And then over time, we see that this first peak actually gets larger and larger and larger. And it turns out when you analyze what's happening or what date these peaks are occurring at, it turns out that this sort of solid blue line is happening right around Thanksgiving. And this dotted or dashed line is happening in Christmas, during the Christmas holidays. So as you can imagine, this first peak refers to Black Friday, okay? And then the second peak refers to Christmas holidays, people just buying, maybe in Boxing Day in Canada, let's say, right? But what's really interesting here is that this time series chains is able to not only find a pattern that repeats, but that is changing across time, but it's also seeing that this first hump is increasing as well. And this is because in around 2007 or 2008 is roughly when the phrase like Black Friday came to be. And so you see this huge spike due to further purchases or search of maybe deals during that period of time. Another really interesting thing to look at is once you've computed the matrix profile is something called semantic segmentation. This is perhaps closely related to what our previous speakers talked about in terms of change point analysis. So in this particular plot here, we're actually monitoring a blood pressure of a patient who is actually lying vertically on a bed. Initially lying flat on a bed, and then all of a sudden that patient's bed is sort of tilted vertically, and this is where you see the blood pressure suddenly change, right? And so the question is, can you find an automated way to actually assign these changes, where the change point is, or whatnot, right? And this actually with matrix profiles, you can actually compute this for free. So as you can see here, there are these patterns that happen when the bed is flat. And then can we actually identify, where we might place this dotted line to separate these two regimes? And you can do that out of the box with STUMPY. So going back to maybe to wrap up on this presentation, obviously you can do many different things, whether it's motif discovery, discord detection. We talked about doing computing multi-dimensional matrix profiles. We also demonstrated about time series change, semantic segmentation, but you can even perform clustering. You can also do shapelets and something called snippets. You can read up on that or ask me for more details, and just a lot more things you can do. And check out the GPU version as well. A couple of calls to action. The first thing is that we'd love for people to contribute to STUMPY, whether it is contribute PRs, even documentation adjustments or corrections is greatly appreciated. Please communicate. Tell us what you're using STUMPY for, and tell all of your friends about STUMPY. And last thing is, nothing makes me happier than if you consider using STUMPY, so consume. With that, again, if you're looking for STUMPY, plug it into your favorite search engine, look for Python STUMPY. All the tutorials that you were just looking at, you can find at tiny.cc STUMPY tutorials. The live demo that you can play around with can be found at tiny.cc STUMPY demo. And then you can also get to that collab notebook at tiny.cc STUMPY collab, as well as the GitHub code can be found at tiny.cc STUMPY code, and then obviously the docs at STUMPY docs. And with that, I'll take any questions, and thank you so much for your time.
Thanks so much, Sean. Can we please give Sean a round of applause in the chat? All right, let me just paste mine in there. So while we are waiting for questions to come in, I did have a couple of things. Like, this is an open source project. You are managing it. Like, being like a data scientist turned developer, what are like some of the lessons you've learned creating this library?
That it will consume all of your time. I think that's sort of it's kind of a sometimes a thankless job. Although luckily a lot of our users are very appreciative of the time that we spend on it, and I try to take it very seriously. But I think it's if you want something to be quote unquote successful, I think that not only do you have to put the time and effort into it, but you also have to spend a lot of time spending time on the marketing side. Right, so getting out there, getting the word out, giving presentations and meetup groups, I think is a great opportunity. Attending conferences, right? But that does take up a good amount of my time as well. So,
do you have stickers?
We actually do. So we'll have to send some over to you.
Yeah, that'd be great. We can definitely pass them around next time we start meeting in person. Also, I'm not too sure if you're able to talk about this, but we had a question if Stumpy has really revealed any insights for TD Ameritrade.
So I'm not at liberty to talk about that, but I can actually at least tell you about some applications. So we've certainly seen a lot of interest in people leveraging Stumpy, especially in the finance world, looking at trading and stock ticker prices. We actually have somebody at CERN who's leveraging Stumpy, so at the Large Hadron Collider, looking at using Stumpy to tune sort of the acceleration of these lead ion particles, and then and stabilizing them, right, and understanding how that might work based upon the time series. Also, we have folks over at Dell who are leveraging Stumpy to analyze call data, so customer call data, which I think is fascinating.
Yeah, it's great, like how the work you've been doing at TD can like affect so many different people. It's like the power of open source. Like, what got you so into open source and like you wanting to create a package that you can release out to the world?
I think it was initially seeing how welcoming the open source community is. Again, being a former academic myself, you always we're looking for things that were for free, right? And oftentimes that open source community has already done a lot of that legwork for you, right? So we have packages like NumPy, SciPy, Dask, Numba to think, and this is sort of one way that we're trying to give back to that community, and hopefully at least we understand how hard it might be to take something that's from the academic world and produce it and package it in a way that is easy for anybody to use, right? So hopefully, if you're using Stumpy, whether you're a scientist or a developer, hopefully it's easy. And if it's not, please let us know.
So it's like, are you trying to make like a Pythonic type of API? Was that like one of the goals?
Yeah, not to give the academic researchers a hard time, right? But even their code, when technically their code is open source, they're very much for reproducibility, but their code was either in C++ or in MATLAB code. And really what I did was I took it out of the confines of the handcuffs of that environment and brought it to where the data scientists are, right, which is really in Python. And oftentimes I think I actually did a poll on Twitter to ask, like, as a engineer, as a data scientist, if you're trying to analyze some data quickly and a package says that it is able to do this, how likely are you to download the code, clone the repo, and install it, compile it, and so on and so forth? And it was basically, I think it was around 75 to 80% of people said no thanks, right? Right. So this kind of speaks to what we're trying to achieve here, right? Is move quickly.
Yeah, like one of my previous jobs, like we were helping data scientists package up their like models and run them on like an Airflow type of system. And a lot of the work I had to do was just like getting the dependencies working. It's like I was building all the Docker containers and just getting that up and running. It's a headache all in itself.
Yeah, not everybody has that. It has the ability to, let's say, spin up Docker and deal with Docker containers, right? And really, we're just trying to make this dead simple.
Yeah, awesome. Also, we did have one more question. I think I'm going to butcher this name. So you mentioned Iman Keog. Do you have
Yes.
any other search terms for finding other applications?
Sorry, other search terms? Oh, for other applications?
Yeah.
Yeah, absolutely. Maybe I'll just show this from the.
Yeah, let me add that screen back.
So, am I sharing right now still?
Yeah, you're sharing.
Okay, awesome. So if you actually Google UCR matrix profile, right, you'll get to Iman's research page, and sort of tucked in down in the bottom here. I mean, I strongly recommend everybody, if you're really interested, check out all these papers. They have around like 20 papers that are published. They're all fascinating, right? But just know that what we've done in STUMPY is implement exactly what is in these papers, right? So that you don't have to. You don't have to reinvent the wheel. But in terms of applications, they have this wonderful PDF down here, which says 100 time series data mining questions with answers. So I recommend you checking out this particular paper because it basically steps you through like all of the different potential applications, which I think is fascinating. I think they're continually adding more and more applications, right? So I strongly recommend it. There's a lot of really fascinating things here. So
that's really cool. Yeah, I'm definitely going to be pasting that link in the chat for later for those folks who need it. I actually did want to ask about your 100% test coverage. So like, so it's like, like, how are you testing STUMPY? Is it like sort of just like computing these profiles for a known matrix or for like a known series?
Yeah, that's a great question. Obviously with the code coverage and unit testing, take it with a grain of salt, right? It's more for my own satisfaction more than anything, right? So believe what you will about what that number means. But setting that aside, with the way that we're testing STUMPY, I think it's quite unique. So the first thing that we do is we obviously have something that's very deterministic. So we have known inputs and known outputs. And really what's interesting here is that we showed the brute force way to compute a matrix profile. So we actually have a naive implementation that we can compare against. So that's actually what we do. So we take a known deterministic input, we compute it using these fast algorithms, and we compare it against the naive output. But what we also do is every time we're running that code, not only do we have a deterministic input, but we also purposely allow for a non-deterministic or a stochastic input. So we actually have a random sampling of a input time series, and we've actually found errors, right, or bugs when we first started, thanks to this approach. So we sort of have a two-pronged approach. And so for every single fast algorithm, we actually have its counterpart, which is what we call the naive algorithm. And so we have a Python module called naive.py in STUMPY. So people can actually see what is actually happening if you break it down.
That's very interesting. I'm really fascinated by this like testing methodology. Have you considered using something like Hypothesis to do like property-based testing?
We for a hot second we thought about using Hypothesis, but I mean, mind you, we're maybe taking next steps. We're not even at the stage of looking at things like integration testing and so on and so forth, right? But with hypothesis testing, I think what tends to happen with hypothesis testing is that you're analyzing sort of individual points, right? Maybe it's a single integer or a floating point or a Boolean, right? In this particular case, our data is just a sequence, right, of floating points. And so there's not really much there. We do have, even in STUMPY, we do have NaN and inf and support within your time series. So that's all possible too. So you can have missing data, so to speak, within your data, and it works perfectly fine. So that's all tested within our work. I mean, if you decide to pass a time series with string characters, that's probably beyond the scope.
Yeah, I guess that should be producing an error in some sort of instance.
Yeah.
So you did mention different ways people can get started contributing. Is there anything that you're looking for in particular?
I think documentation, I think, is the greatest thing. So considering that in STUMPY, we actually try very hard to be inclusive, right? And all of our tutorials actually reproduce some of this, all of this academic work that I showed you back here, right? All of these, some figure in one of these papers. And oftentimes it'd be very helpful if somebody wants to contribute, the reproduction of one of these works, or just to engage with us on in our GitHub issues. We try to be exceptionally transparent. We try not to hide behind some hidden like Slack channel, let's say. So everything is out in the open. All our conversations are on our GitHub issues. Feel free to post anything up there, ask us questions, and contribute what you think will help make us better.
That sounds fantastic. For contributors, is it mostly folks from TD Ameritrade? Have other companies started making contributions?
Yeah, we've had a handful of folks. In fact, some of our earlier contributions was somebody that was out in Sydney, Australia, that helped us get our continuous integration up and running. We got folks here at the University of Michigan that were helping out. Shout out to Bradley Dice. Also, you mentioned the folks over at CERN who are using it. They're definitely heavy contributors back to STUMPY. And so we're seeing a good amount. And even people, again, I think contributions even to improving documentation is really what is just as valuable as the core code.
Yeah, I think that was sort of the way I first got started, and it's like it means so much because that's the first place people go for help. And if you have poor documentation or something that's not very clear and not reproducible, it adds just such a hard like a barrier people can't cross. So yeah, definitely give a shout out to documentation. All that work is definitely underappreciated. So do you have anything else you would sort of just like to mention about STUMPY that we sort of have not covered?
No, I think that's about it. Again, get out there, use it, provide feedback. Always happy to hear back from users.
Awesome. And can we get another round of applause for Sean in the chat? But before we do let you go, is there a call to action besides going out and using STUMPY?
Yeah, just a reminder, PyData Global is coming up. So make sure that you get your proposal in for a talk by August 2nd.
Awesome. And I will also add that to our Slack channel. We have a call for proposals channel. So join that to get latest information for CFPs. I want to say thank you so much, Sean. This was a very fascinating presentation, and I definitely learned a lot.
Yeah, thanks so much, Ollie, and thank you, ChiPy.
Yeah, we'll see you around.
See ya.
All right, so that was Sean Law talking about the package STUMPY for building out matrix profiles for TimeSeries information. Let me just share my screen, and we can just wrap up the rest of this meeting. So we do have some announcements. Let me just get give me 1 second. Yeah, we recently revamped our mentorship program. Before it used to be a more structured program, but this has become like we sort of just changed that model. So we released it a couple of weeks ago. It's called the Buddy Mentorship app. So it's a little bit more self-directed. You go create a profile about what you know, what you want to learn, and then you can send mentorship requests to different people. And then we're sort of expecting folks to build out these informal bonds using platforms such as Slack. Yeah, so just shout out one more time, chippymentor.org is that website. So we do have some upcoming events. Tuesday, August 4th is going to be our next WebDev/DevOps event. There's going to be a talk on Flask and a talk on project management. Our next AlgoSig is going to be on Thursday, August 6th. And our next Dunder main meeting is going to be on Thursday, August 13th. We have a talk by Piper Thurmstrom about building sustainable communities. She's going to be talking about what they've done for Pursued PyBear game development library. So where can you find more information about ChiPy? You can connect on our Slack. Hit up that URL, join our workspace. We have around 2,000 members talking about all interesting things in Python. We also have fun channels like Pets of ChiPy. You can find information about what's going on in Chicago on our Twitter, and all this information plus event information about what's going on, links to our like sponsors page and things like that is going to be on our website. Well, that's pretty much it for us. Thanks so much for sticking around. If you're still here and you had a good time, go down below and hit that like button. And if you haven't done so, subscribe to our channel, hit the bell icon, and you'll get notified for our upcoming events. So my name is Ali Sivji. That's it for us at Chicago Python Data SIG. We'll see you next time.